Welcome to CSI Training. Our mission is to impart the information, techniques, and confidence to successfully apply RBM, reliability-based maintenance technologies and products. Thank you for joining the thousands who have recognized and selected CSI Training as the world leader for quality instructional products. The next 40 minutes will reveal the keys to implementing a successful lube analysis or tribology program. Whether your plant practices preventive, predictive, or proactive maintenance, you will be able to apply the tips and techniques presented here to strengthen your reliability-based maintenance program and save thousands of maintenance and downtime dollars. The study of the lubrication of interactive surfaces in relative motion, such as bearings or gears, is called tribology. So oil analysis programs usually are called tribology programs. The tribology information presented here is not targeted toward the chemist, but to the maintenance technician or plant engineer who must ensure proper lubrication of the machinery for optimum performance and ensure proper management of the lubricants. Some maintenance programs regularly collect oil samples and send them off for analysis, but when the results arrive, the only part read is the one line of recommendations. Then it is simply filed away because a plan is not in place to use the results, or due to a lack of training, the report is not meaningful. But the lab report is only as good as the information supplied to the lab. We will consider how to develop a plan to use lubricant analysis as a means to detect lubrication problems and mechanical problems, as well as diagnose the source or cause of premature machinery wear. We'll look at oil and machinery conditions that can be diagnosed with on-site lab and with off-site labs. Steps and techniques are shown to collect oil samples and perform tests for certain conditions, and recommendations are made for off-site tests. Then, methods and rules of thumb are shown for setting alarm levels for the various machine parameters and machine types. First, let's look at oil analysis and see where it fits into your maintenance program. There are four basic philosophies of maintenance, and we can compare them using a typical example. If a machine is misaligned, excessive force is applied to the bearings, which will cause them to fail prematurely. One maintenance philosophy approaches this situation with a "if it isn't broke, don't fix it" attitude. This is reactionary or run-to-fail maintenance, which is often referred to as hysterical maintenance. When the machine fails, it is usually catastrophic and will then be fixed. Analysis of oil or lube samples from the failure is really post-mortem analysis and will have excessive wear particles, contaminants, and may be degraded due to excessive heat. The second maintenance philosophy avoids these catastrophic failures by looking at the machine from a historical perspective. If it tends to fail every 18 to 20 months, then replace the bearings every 12 to 14 months to prevent a catastrophic failure. This philosophy is called preventive maintenance. Oil analysis programs and preventive maintenance plants tend to only replace the oil at calendar intervals, with the lab reports of the oil condition really having no effect on the maintenance program, and valuable information on machine condition, lube performance, and contamination is lost with each oil change. With the advent of electronics and computer-aided technology, instrumentation has been developed to detect and trend characteristics of failures, such as bearing failure, to get the most life from the machine by replacing it only when it is in progressive stages of failure. Accurately predicting the time of failure can save thousands of dollars from premature replacement of the components. This predictive maintenance philosophy is actually much more involved than condition monitoring and uses many technologies such as vibration analysis, infrared thermography, motor current analysis, and oil analysis to determine the present condition and predict the future for the machine. Predictive maintenance programs have proven savings of millions of dollars in maintenance costs. Oil analysis in a predictive maintenance philosophy capitalizes on the program with early diagnosis of problems, which in some applications go undetected with vibration analysis. Thorough training coupled with precise steps of action for specific lube conditions can be the lifeblood of a predictive maintenance program. Substantial savings are realized from adding oil rather than replacing oil that still has useful life, and consolidating oil types for various machines. Additional savings result from reduced waste oil disposal costs. The fourth maintenance philosophy questions why the bearings are not running to a full life expectancy, which can be from 5 to 20 years. It then identifies and eliminates the source or root cause of the accelerated failure. In our example of the misaligned pump leading to early bearing failure, the problem would be corrected by performing precision alignment and not just replacing the bearings before they fail. This is a proactive philosophy, requiring a mature management environment which has detailed control, performing cost benefits, certifying new equipment and lubes, providing technical training, and linking all technologies. A proactive philosophy results in dependable maintenance operations called reliability-based maintenance. To achieve this RBM approach, the vibration analyst also has a working knowledge of tribology, with on-site capabilities as well as an electronic link to an off-site lab for results and a direct link to a computer maintenance management system for immediate responsiveness. Oil analysis in a reliability-based maintenance environment has the greatest potential for savings because the root cause of oil contamination, degradation, and machine wear is searched for and corrected to achieve maximum life for the machine and the lube. To achieve these optimum results and avoid a meaningless loop, your plan must have a purpose with specific pre-planned actions for particular events that will lead to the goals of improved lubrication quality, reduced machinery wear, extended oil change intervals, reduced oil disposal costs, and reduced oil sampling costs. The plan begins with identifying machines and processes which are critical to plant production or critical from a safety standpoint. Next, document the lube type and the environment it is used in. Then establish alarm limits and target cleanliness levels along with the required oil testing appropriate for the machine type and lube type. Train all personnel involved so each one will have the big picture of the lube analysis program, as well as the specifics for proper sampling, handling, and testing of the lubes. Now you are ready to jump into the loop, shown earlier, but provide more steps and exits from the loop. The first step in the loop is collecting proper samples. Then screen the sample for extreme conditions using on-site capabilities and well-trained personnel. If necessary, send the sample to an off-site lab for additional diagnosis. If additional diagnosis is not necessary, bypass this step and store the results in a computerized database. Obtain the off-site report and store it in the database. The next step is most often ignored or overlooked, possibly due to inadequate training. Compare the results and trends with complementary predictive technologies. Comparing trends of vibration data of bearing frequencies, for instance, along with trends of iron in the oil viscosity, and large particles can confirm the bearing condition. If temperature data is available, its trend could also provide useful information. Based on these findings, schedule any necessary maintenance and generate management reports. Although this is often the end of the loop, to build the program on a reliability-based maintenance philosophy requires you to exit the loop and use all the gathered information to remove the root cause of the problem, improve the quality of the lubrication, reduce the wear on the machine, and avoid catastrophic failures. When collecting oil samples or handling new or used oils, remember to follow the standard practice procedures for health and safety established by your company. A key factor in oil condition monitoring is consistency in collecting samples. Any oil monitoring program will fail if careful attention is not paid to sampling technique. For that reason, sample from the same location in the same manner and under the same machine conditions. In general, oil should be sampled from a location where the oil is well agitated or flowing. Take samples just after the equipment has been shut down or when it's safe while the equipment is operating. It is important to sample before particles and water have time to settle out of the oil. Samples should normally be taken upstream of any filter. If the oil is sampled on the downstream or outlet side of a filter, the debris and particulate contaminants will have been removed by the filter. Please remember to always consider safety when sampling hot oil from running machines. Because on-site tests are relatively inexpensive and under your direct control and interpretation, be creative and don't be afraid to tailor unconventional sampling techniques to your specific needs. Just remember to apply common sense in correlating your sampling technique and test results to your application. When drawing oil through a drain plug or valve, don't collect oil during the initial spurt or rush. It may contain metal from the plug threads, and it will certainly contain debris that is collected over time around the plug or valve opening. Don't take the cap off the clean sample bottle until you are ready to take the sample. As soon as the sample is taken, replace the cap. This will help to keep the dust, moisture, and dirt out of your sample. Fill the bottle about half full. This makes it easy to completely mix the sample by shaking prior to testing. When using a suction pump to draw oil up from a sump through a fill pipe, dipstick tube, or other orifice, don't let the plastic tubing scrape dirt from outside the orifice or from the bottom of the sump. On the other hand, if you are concerned about free water in the system, go ahead and sample from the bottom of the sump. But remember, always change or clean the sampling tube between samples. As a general practice, you would not want to initiate a maintenance action on the basis of an oil sample taken directly from a used oil filter. However, this is where you will find the highest concentration of solid contaminants and large wear particles. If the filter is free of metallic debris, it is unlikely that much wear has taken place since the filter was last changed. Label each sample bottle with the oil type, the machine from which the sample was taken, and the sampling date. If a sample is diluted prior to testing, the label should reflect that fact. A sample taken from an unknown source has no value. Mislabeling of your sample might lead to unnecessary and costly maintenance actions. These samples hold a lot of information about the oil and the machine, but special testing is required to get that information from these samples. Oil analysis can be compared to the analysis of blood samples in the medical profession. If all that's needed is blood type, then one simple in-office test is performed. However, there are over 900 specialized tests for blood to determine the presence of particular antibodies and diseases, germs, chemicals, and bacteria. But usually only a few tests are run on any person, with the most advanced tests being performed in an off-site lab. Machinery lubricants can be analyzed similarly, and for each machine, there may be only a few tests required. And like blood tests, an instrument produces specific results, so many instruments may be required for multiple tests. These devices here are tools commonly used for on-site oil analysis. Each of these is designed to provide particular information about the oil. There are two categories of information testing provides. One is about the condition of the oil itself, and one is about the condition of the machine. For the oil, you want to know the lube quality, including the condition of any additive package, if there are any contaminants, and whether it is the correct oil for the particular application. The machine condition is determined by examining the wear particles for size, shape, and the materials such as ferrous and non-ferrous metals. Various systems and applications require different lube conditions, such as hydraulic systems and machine tooling, which require exceptional cleanliness, and gearboxes, which by their very nature tend to produce more wear. These applications require particular oils and additives, especially suited to the demands of the system, and should have different standards of cleanliness. The most important parameter of a lubricant is the viscosity. Viscosity is the measure of a fluid's natural resistance to flow. Oils flow more freely at higher temperatures and are resistant to flowing at lower temperatures. So the measurement must take into consideration the fluid temperature when measured. Viscosity is measured in centistokes at the temperature in degrees centigrade. There are tables for the viscosity of each oil at 40 degrees centigrade or 104 degrees Fahrenheit and 100 degrees centigrade, which is 212 degrees Fahrenheit, or the boiling point of water. When the viscosity at 40 degrees centigrade and 100 degrees centigrade is plotted on a special scale, then the viscosity at any temperature can be calculated and then compared to the sample to determine whether it is the correct lube for the machine. Each machine has characteristics that demand a particular lube viscosity for optimum performance. High-speed machinery must use a low viscosity or lightweight oil, while the lube of slow-speed machinery should be higher viscosity or heavier. Since the lube should provide a film between internal components, heavier loads such as gearboxes require a heavier oil. Light loads require a light oil, and if a heavy oil is used, extra energy is required to move the components, producing heat and degrading the oil. High temperature applications require higher viscosity or heavier oils than colder operating temperatures. Viscosity must be adequate to separate the moving parts at the operating temperature of the machine. When a machine must operate in both cold and warm temperatures, such as outdoor applications, an additive package called a viscosity improver can be added to the oil to make it perform suitably in both environments. If an oil has a viscosity of 17 at 100 degrees centigrade, it may have a viscosity of 140 at 40 degrees centigrade and a viscosity of 1800 at the 0 degrees centigrade or the freezing point of water. The 17 may be acceptable, but when the machine must be started in cold weather, the oil is too heavy. The viscosity improver does not affect the value at 100 degrees centigrade, but reduces the viscosity at the lower temperatures. Oils such as this are referred to as multigrade oils and are commonly used in automobile and truck engines. The viscosity of an oil in a machine is a key to quickly determine whether the correct oil is in the machine. An on-site oil analysis should have the capability of measuring viscosity. Methods of measuring viscosity include timing the flow through a calibrated capillary tube heated to 40 degrees centigrade or 100 degrees centigrade, timing an object to fall through oil, and measuring the drag on a disc spinning in the oil. This digital viscometer uses a patented free rotor system to measure viscosity and the oil temperature, recording the information in a database to be used in conjunction with other analyzers and devices to trend your oil condition. Compare this measured viscosity against the machine manufacturer's recommendations and against new oils to verify they are correct. Oil viscosity in a machine can change due to chemical, mechanical, or process influences in the system. Viscosity increases due to oxidation, foaming or cavitation in a pump, emulsion with water, solids contamination, and the wrong makeup lube added. Decreases in viscosity are caused by fuel or solvent contamination, refrigerant leaking into the system in air conditioning systems, non-emulsified water contamination, molecular sharing or chemical breakdown, and the wrong makeup lube added. A change in viscosity of 10% is a good indication of a lubrication problem, and checking viscosity is the simplest and quickest method to check for a wrong lube. Maintaining lube quality is a key to ensure consistent, smooth-running machinery. Degradation removes the lubrication properties and may destroy some of the additives. The primary sources of oil degradation are oxidation, sulfation, nitration, and soot loading in diesel engine applications. These all increase acidity and deplete additives. Oxidation is any chemical change due to interaction with oxygen, usually in the presence of heat. Iron oxide, for example, is rust. The effects of oxidation are seen as the sticky residue lining in the sides of oil storage tanks. This gummy residue is called varnish. Sulfation is a chemical reaction with sulfur and is usually found only in diesel engine applications. Soot as a byproduct from combustion process is also usually present. Nitration is the chemical reaction with nitrogen. Oxidation, sulfation, and nitration all increase the viscosity, darken the oil to a reddish-brown color, and increase the acidity of the oil. The increased acid in the oil causes corrosion to your machine, so that instead of protecting the machine, the oil actually accelerates degradation. To check the oil quality for degradation and any other gross chemical changes, the OilView analyzer compares a used oil sample with a clean oil sample of the same type used in that application. The changes in the oil chemistry are detected capacitively by the OilView sensing grid. A full test must be run on the new clean oil as well as the used oil because, unfortunately, the new oil samples sometimes have dirt and water, and must be inspected periodically to ensure harmful contaminants are not being introduced into the system. When the new lube is tested, it is recorded in a database for easy retrieval and comparison with future samples. After proper setup, used oil samples are well shaken and tested for 500 seconds, or about 8 minutes, comparing the results to a reference oil. The comparison of the two can be displayed graphically and are noted in the indices with recommendations reported in the automated diagnostic function. This analyzer provides a good indicator of any chemical changes that result from soluble fluid contamination, increased acidity, the occurrence of oxidation, sulfation, and nitration, as well as the presence of soot. The on-site tests for lube quality provide instant results assuring you of the vital functions of the lubricant. We have seen that we can perform on-site tests to verify that a lube is the correct one and to determine any chemical degradation that could lead to a loss of performance. There is another area of concern about the lube that should be analyzed, and that is the presence of any contaminants. Contaminants include any foreign particles from outside the oil system getting into the oil. These include water, fuel, coolant, dirt, dust, processed fluids, and other solid or fluid contaminants. These particles range in size from 1 micron up to several hundred microns. A micron is 1/1000th of a millimeter, which is about 1/25th of a mil. Human hair is 75 microns, and the unaided eye can see objects as small as 40 microns. Precision valves and pumps have clearances of 25 microns or less, and the thickness of the oil film in a bearing under heavy load can be less than 1 micron. Since bearing clearances can be so small, even minuscule particles in the lube can cause severe damage to the bearing surfaces. Detection of these in the oil can be performed on-site with 2 instruments. One is the 5100 analyzer, and the other is the 51PC particle counter. The analyzer tests for water, coolants, and other fluids, while the particle counter uses a laser beam to detect and measure the size and number of solid particles per milliliter of oil. They are categorized in size ranges of 2, 5, 15, 25, 50, and 100 microns. Studies show that the cleaner the oil, the longer the machinery will last. Therefore, it is important to continually increase the cleanliness levels of critical equipment. A typical sample may have many particles in the 2 to 10 micron range and not be abnormal. There are 3 rules of thumb concerning particle contamination. First, for most mechanical systems,